Then we'll have, here we go. And then at the end of the talk, we'll have a chance to ask a few questions. So yeah, Juan, please take it away.
Okay, hello everyone. So let me quickly introduce Tarek. Tarek is, let me go back in history. He did his PhD thesis at Tense at the High Energy Physics group. That was in optimizing the configuration of CTA, of the CTA telescopes, both north and south, using Monte Carlo. So that was his introduction into the field of Cherenkov telescope, Cherenkov telescopes. It's also relevant. He was in that group, and that group developed some hardware to do actually fast photometry with Cherenkov telescopes, fast photometry in optical. So he was already getting some experience in that. He then moved to E5 with a postdoc and Juan de la Cierva fellowship. So he spent a couple of days, I believe, at E5, working again in gamma rays, very high energy gamma rays with Cherenkov telescopes, CTA and MAGIC. Okay, he started more interested on doing also photometry with Cherenkov telescopes, going to the stellar occultation beam and measuring the diameters of stars in parallel to a standard gamma ray analysis. Then he moved to DESI, where he started to work in the VERITAS group of DESI. You know, the big telescope collaborations right now are Cherenkov telescopes collaborations are MAGIC, VERITAS, and HESS. He was working in VERITAS for a while, again in gamma rays and optical studies. And finally, he made the wise decision to come to CIEMAT with an Atracción de Talento fellowship. His regional work is now. He has now joined again the gamma ray group, working in CTA and MAGIC. So today he'll be introducing some of the stuff he's doing with the new MAGIC interferometer and CTA, the prospects for CTA. I guess you can go ahead.
Thank you, Juan. So if anyone can just confirm that you can see the slides right, and that you see them, in full screen now.
Yes.
Okay. So thank you, Juan. Indeed, I'm very happy to be back in Madrid, and very happy to belong now to CIEMAT. I don't know that many people at CIEMAT yet, as we were talking just before, because the situation is just terrible to meet new people. But hopefully soon I will be able to know more people at CIEMAT. Anyway, so I'll be talking about different uses that you can give these telescopes, specifically on topic of measuring the size of stars. Okay. So the specific topic that I will be discussing, it will be very general, but I will be always talking about milliarcsecond and sub-milliarcsecond resolution astronomy. Okay. In the optical and also a bit in radio, but to really understand what this topic is, one needs to understand the units, and this milliarcsecond is actually a very small unit that is hard to understand. So what does really a milliarcsecond mean? Okay, so let's assume that the Earth is flat, just an assumption for now, and think yourself in a window in New York, and looking to, okay, so if you put a coin in the Eiffel Tower as seen from New York, that would be 1 milliarcsecond. Okay, so it's an extremely tiny angular extension. So that tiny extension is actually the size of the stars, the angular size of the stars that we typically see in the sky. So the very bright ones. Here I just show some examples. So either the moon or the sun are on the scale of 30 arc minutes. Then the planets are on the scale, or well, the big ones, they are on the scale or 30 arc seconds. Okay. Then the very largest stars that we know, so very close and extremely large, are on the order of milli-arc-seconds, no? So tens of milli-arc-seconds. But the typical bright stars that we see in the sky, and with bright stars, I generally mean the naked eye stars, they are on the order of 1 milli-arc-seconds. Okay, so either studying the structure of stars, so not just seeing a single dot, knowing how large it is, for example, trying to see some structure on other stars than the sun requires going beyond this milli-arc-second resolution. Okay. Also, if you want to go for smaller stars, then obviously you also need to go beyond the milli-arc-second, because milli-arc-second are really the bright ones. Okay, and the relatively close stars. So the way that we know that we can reach this extremely small resolution is with interferometry. Okay, this is the technique that allows modern observations to reach these angular resolutions. And we will go back to this plot many times along the talk, so it is important that everyone understands it well. So here, the x-axis is essentially broken to realms. This is wavelength. So at the left you have the optical, and on the right you have the radio. Okay. And the golden message that I want you to remember, even if you don't understand anything about interferometry, the key thing here is this equation, very simple one. The resolution that you reach with interferometry proportional to wavelength of the light that you are observing divided by the baseline. And with baseline, we mean the distance between telescopes. Okay, let me discuss, introduce the topic of interferometry. So it will be a very gentle introduction that anyone should be able to understand. I will not go into the technical details because they are really, really hard to understand. Okay, the principle of interferometry, and probably what most of you know about interferometry, is simply a technique that allows different telescopes to work together and to simulate a telescope of the size of the combined different telescopes regarding their distance. No, so here I show a very nice mock description of the interferometry of the Keck telescopes. These are telescopes. Each of the telescopes is 10 meters, but they are separated. So when they operate as an interferometer, the equivalent angular resolution that they are able to reach is that of a telescope of 85 meters in diameter. We always refer to the diameter because it's the value that limits angular resolution of an actual telescope, of an actual optical telescope. So I will again be very vague, but this interference that the different telescopes are measuring, and then they combine. So the interference on the waves that both telescopes measure carries the information of the high resolution shape of the observed source, but some information is lost. Okay, so it is essentially impossible to do a perfect image unless you have a perfect coverage of the UV plane. I'm becoming technical, but you just need to remember that this technique is by far not perfect. Okay, a lot of information is lost on the way. I will go back to this point later, but so there are different different ways to measure this interference using telescopes. Currently, the most common ways are with optical interferometers. They literally physically combine the light from both telescopes, and then when you are you measure the actual resulting amplitude. No, so you are literally combining waves and measuring the combined amplitude. While in radio, the technique has evolved dramatically, and now telescopes only need to be linked electronically. So they either physically linked electronically or even offline. You can essentially download the data and combine later. So now in radio you can combine any telescope in the world with, as long as it makes sense, of course. Anyway, so the pros and cons. So it's the actual only way we know to reach such angular resolutions. Of course, you could take one telescope to, for example, the Hubble Space Telescope has really good angular resolution, but interferometers on Earth have clearly better angular resolution, as I already showed in this angular resolution plot. But the technique is clearly not ideal. Okay, so the sensitivity is very limited. So the individual telescopes will detect much better the actual the stars operating independently. But if they operate as an interferometer, the sensitivity significantly goes down. Why? You could actually, let me go back a couple of slides. You could imagine that this 85-meter telescope is clearly not detecting all the photons from the simulated 85-meter dish. You know, it's only detecting a very small amount of photons. So you could imagine that if you a measurement coming from this 85-meter telescope, then to gather enough data to have actually enough photons. Also, something that is really hard to understand for the non-interferometry experts is that the only scales, angular scales, I mean, that you are able to study are those that you actually cover with telescope pairs. So each baseline that you cover, so if you have two telescopes that are correlated on wavelength, they are studying a fixed angular resolution in the sky. So if you only have those two telescopes, then you are studying a fixed angular resolution in the sky, meaning that much bigger stuff and much smaller stuff, you are simply blind to that. Okay, I added some backup slides. One backup slide that very nicely shows this effect. You can go back to it later, or simply ask later, that we will hopefully have some time. Okay, so going back to this plot, I will briefly introduce the currently the state of the art of the long baseline interferometry in the optical and in radio. Okay, let me go very briefly. So Chara, the Chara array you here, it is a system of several optical telescopes. The maximum separation that they have is 330 meters. Generally, they observe in the red, okay, and in the infrared. So this telescope, they were able to do some amazing studies. They have been properly imaging telescope stars, fast rotators. They actually detected the occultation of a star from a gaseous structure in these photos that are absolutely amazing. Here I show how the telescopes are literally physically with vacuum pipes that actually carry the two light beams from telescopes that are being used for the interferometer calibration, for the getting that interference. So VLVA and EVN, they are essentially a link most of many large radio telescopes all over the world. Okay, so here you can see those belonging to VLVA, those belonging to EVN. Benito Marcote is here in the call, so he will gladly answer any question about VLVA and EVN. So again, all these telescopes working together are able to reach those resolutions that I was showing here. Okay, so this resolution is actually limited by the actual size of our planet, and the same goes for the Event Horizon Telescope, which you have probably already heard. They were able to perform these images of the shadow of a black hole, and they are essentially the same. They essentially use the very same principle as the one that the VLBA and EVN use, but going to shorter wavelengths. Again, if we go back to this figure, remember that the resolution improves if you go to shorter wavelengths. So if your baseline is fixed, for example, in the case of radio telescopes, the baseline is fixed. Our planet cannot be bigger unless radio telescopes to space. So with the actual size of our planet, this is the resolution that we get in radio. So if you go to shorter wavelengths, then you get the Event Horizon Telescope. Okay. And this is precisely why optical interferometry might be interesting, because with much smaller baselines, for example, here I'm showing that with 100-meter baselines, you are already getting the same angular resolution that a radio telescope of the size of the whole planet gets at a given wavelength in radio. Okay, a rather long baseline, long wavelength in radio. So this is what I wanted to show. Telescopes significantly closer to those in radio provide very high angular resolution because they are measuring optical photons. Okay, this is one of the important messages to understand optical interferometry. Now I'll be talk about this blue shaded region here, which is the Narabri Stellar Intensity Interferometer that you can see in this picture. So Humphrey, Brown, and Twist, they were the people behind this project. They developed the Humphrey, Brown, and Twist effect, which led to the first intensity interferometer. You can see here the two telescopes that they used. They were mounted on a circular rail, so they can actually modify the distance between the two telescopes, between 10 meters to, I don't remember, to 200 meters, no, to 120 meters, something like that. Sorry, I don't remember. So each telescope was 6.5 meters in diameter, and they were able to, in the 60s and 70s, to measure the diameter of 32 stars. This was unprecedented. Amplitude interferometry was not at the stage to reach to these results, so it was remarkable. So they demonstrated that you can actually perform interferometry measurements combining the actual time evolution of a signal. So not directly the amplitude of the light waves, but actually the evolution of the combined signal. So this technique essentially disappeared because it provides rather low sensitivity when compared with modern amplitude interferometers. No, so what I was saying before, VLTI, Keck, Chara, they all use amplitude interferometry. And the reason behind it is that this technique requires enormous mirror surface and extremely fast electronics, which at the time were clearly not available. No. Okay, so the basic theory about this, again, I'm not going to become very technical, but because on a thermal source, you can imagine that different parts of the source are emitting, have different fluctuations. No, so if you have to observe at a given distance t, then you will observe the same fluctuations as long as you are as the distance is much than lambda over the actual size, angular size of the star. Okay, so the main message that you need to remember is that now what we are correlating is the time evolution of different parts of the star. No, so well the coherence of the combined waves having different fluctuations. So sorry, I'm getting a call. Okay, so more basic theory. So why you need very large mirror surfaces? The reason is because the actual coherence, which is extra term that will appear when both telescopes are close enough with respect to the wavelength to see this enhancement of the signal, is extremely small, is on the order of 0.01%. of the signal. This means that statistics of that you need to measurement of such a tiny effect, which is this coherence term here, essentially needs enormous mirrors. And the last bit of basic theory that I need to introduce is this formula here, which is that we all need to remember by heart if we work on this. So this is the signal to noise that you get from an observation using stellar intensity interferometry. And the terms that are more relevant, so here these two terms account for your efficiency to catch photons. This term here accounts for the mirror area of the telescopes. Of course, the star visibility, I will not talk much about visibility, but it's essentially the measurement that you want to do, what is the degree of coherence depending on your baseline. And here you can see the square root of B, which is the bandwidth. So then, of course, you have the observing time and your filter quality, noise, etc. But the two messages that are important is, first, we need enormous telescopes because we need many photons to actually perform a measurement of that tiny coherence. Second, because you are trying to correlate fluence, the faster you measure, the faster you sample, the better. Your signal to noise significantly improves. No. So now let's talk briefly about what atmospheric Cherenkov telescopes are. Okay, IACTs, imaging atmospheric Cherenkov telescopes. So you can clearly imagine them both as particle detectors and optical telescopes. Okay, so this is the plot we always show. This is the full electromagnetic spectrum, and this is the altitude at which most of the photons are actually blocked by the atmosphere. And the range that we study with these Cherenkov telescopes is this one here. Very high energy gamma rays are definitely too energetic to reach the surface of the ground, but that's fine because when they collide, they have so much energy that they produce a cascade of particles, and within those particles you have electrons and positrons. In an electromagnetic cascade, it's mainly gammas and electrons and positrons, and those electrons and positrons are going so fast in the atmosphere that they emit Cherenkov light because they are going faster than the speed of light in the medium. And that Cherenkov light is blue. Okay, so so you can imagine that that one very high energy gamma ray is coming from the crab, for example. It is a gamma ray, and it holds the impinging gamma ray has, for example, 1 tera electron volt of energy. It produces a shower of blue light that is generally 120 meters in radius, more or less. We don't know the direction and energy, and we don't know anything about this shower. No, so if we put a single Cherenkov telescope within the light pool, then we get this kind of rough showers, and we are able to reconstruct following these parametric, what we called this parameterization here. We are able to reconstruct the actual one of this vector. So you can essentially say that this shower is within this plane. Okay, you can also do a mono analysis, but generally with just one telescope you normally don't get enough information from this gamma ray. But if you add more telescopes within the light pool, then you have different points of view of this same shower, which means that you will be able to take different pictures, different photos of this distribution of electrons and positrons, and then you will be able to properly calculate the intersection between this plane and properly reconstruct the impinging shower direction, energy, and hopefully to identify it as a gamma ray. No? Here I just show some I should not have included here. Apologies. But anyway, so when you have several Cherenkov telescopes detecting the same showers, then you're really able to reconstruct the direction, the energy, and to identify it as a gamma ray or cosmic rays, etc. So, as I already said previously, we are actually detecting is not gamma rays. What Cherenkov telescopes detect is blue. So they are optical telescopes. No, here I just show the examples of MAGIC-VERITAS on the right and HESS at the bottom. HESS is in the southern hemisphere, and both MAGIC and VERITAS are in the northern hemisphere. So these are the main current generation telescopes, and they all are optical telescopes, meaning that they detect optical photons. If you think of an imaging atmospheric Cherenkov telescope as an optical telescope, then you can see that physically very similar. So they have a mirror surface, they have a camera in their focal point. There are other telescopes, optical telescopes, that also have cameras in their first focal point, but most of them have them in the second focal point, or even in the third focal point. But anyway, so here, for example, I'm comparing with the Subaru telescopes. It's a 8.2 meter telescope that costs roughly $350 million, while I'm not going to say what's the price of MAGIC-2, I think it's in this case, but probably roughly 2 orders of magnitude cheaper. Okay, why is it cheaper? Well, I'm not saying it here, but essentially because the quality of the mirrors is lower, the camera is cheaper, and as you can see, we don't need any building, and the structure is simpler, etc. We don't have the same requirements because all we want is those rough images of the photons. But if you imagine these telescopes as particles, if you compare them, for example, with the Fermi-Lab telescope, which has this classical tracker to actually make sure that your gamma ray interacts with your detector, so that you produce electron-positron pair, and then with the calorimeter you measure the energy within these from particles. No, we have essentially we do the same thing, except that the tracker is the atmosphere itself, and the calorimeter, more or less, is the telescopes that you put within the light pool. No, as calorimeters, we are not very good because we are clearly not detecting all the light that from the light pool, but the principle is very close. No, so of course, having atmosphere being part of your detector brings a lot of, but this is what we do, and of course we rely on Monte Carlo simulations to be able to understand this process. No, to be able to do a high-level analysis, you absolutely need in this technique Monte Carlo simulations, because direct calibration is not possible. So Cherenkov telescopes as optical detectors, they use photomultiplier, which as optical physicists you probably know what they are, and they measure signals that are of nanosecond scale. This means that they observe in very high frequencies, in gigahertz frequencies. So because these flashes of light are very faint, then you require very, very large reflecting surfaces, because we don't really require to know exactly where each electron-positron pair are, just need the direction of the shower. The mirrors and let's say the quality of the build of the telescopes is not of astronomical quality. Astronomical quality would be way more expensive. So here I just show how large are Cherenkov telescopes compared to the main optical telescopes right now in the world. So here, for example, you can see Keck here, and you can see here VERITAS, or you can see here the large size telescope, which is the first prototype that is already installed in La Palma. You can see here that in terms of just size, Cherenkov telescopes are indeed enormous, are largest. So once CTA comes, if you sum up all the mirror surface of CTA, you would get this, which is absolutely enormous. No, so purely serendipitously, IACTs are almost ideal to perform intensity interferometry observations. Okay, they have enormous mirror surfaces. Even if their optical efficiency is not very good, they compensate it with more and more mirrors. No, they have an enormous mirror surface. The bandwidth, they can actually go extremely fast, and remember, the faster you sample the signal, the more signal to noise you will have in your intensity interferometry measurements. the optical design, as they have been designed to measure extremely fast signals, the nanosecond scale showers, they are already designed making sure that they keep the isochronicity of the signal. So a single pulse of light will reach the focal point at the same time, no matter where you hit in the telescope, of course, more or less. And also they come in arrays. So we will already have several telescopes to be able to make to make correlations between the telescopes. No. So going back to this plot again of angular resolution as a function of wavelength, we could actually, if MAGIC operates as an interferometer, we would be actually sampling this region here, meaning that we would be essentially our limiting angular resolution would be essentially the state of the art right now, equivalent to charas, but going to the blue color. So this is essentially a territory that has not really been studied much, other than the Narabri telescopes in the 60s. Although our sensitivity would be way better than the Narabri telescopes, because our telescopes are larger and because we sample faster. No. So the truly exciting fact about demonstrating that this technique works for Cherenkov telescopes is actually thinking for the future of Cherenkov telescopes for CTA. No. So if you look to the future, then you will have CTA, which will have hundreds of Cherenkov telescopes at distance between 100 meters, 80 meters, and 2,000 meters. And actually, technically, it's not that difficult to convert these telescopes into an interferometer. No. Also, a very big pro of implementing this is that stellar intensity interferometry observations are actually possible during bright moonlight, and during those periods, it's very common for Cherenkov telescopes actually not to operate, not to observe. You could imagine that these observations would come for free. No. So if you want to take a look to some of the science cases that you can study with CTA as a Cherenkov as an intensity interferometer, you can go to this reference. So this is not very precise, but this is essentially the angular resolution that you could reach with CTA as an stellar intensity interferometer. Okay, we are literally creating an optical equivalent of the EVN, even almost the Event Horizon telescope, by equipping the CTA with this extra feature. Okay, so so is this possible? So can we actually demonstrate that these measurements are possible with Cherenkov telescopes? So this is something that CIEMAT has actually played a leading role on. So in the last few years, CIEMAT was able to actually prove that this works for MAGIC. They built into the moon filters of MAGIC an actual case for putting there a low passband filter. Then they correlated the signals from the two telescopes using literally an oscilloscope, and they were able to measure this nice signal that you hear and that they published last year. And this was literally the first actual proof that Cherenkov telescopes can indeed operate as intensity interferometers without enormous modifications. Okay, they are using the same as the standard MAGIC pixels, and the sensitivity that they showed is actually very good. So the answer is yes. So these telescopes can indeed operate as interferometers. At the same time, it is fair to say that VERITAS also did the same. I was part of VERITAS at this time, and we were able to publish these results in Nature Astronomy. And essentially, because VERITAS has more telescopes, then you get correlation measurements. So you are able to measure a wider range in baselines. I will not be discussing a lot about these plots that I'm showing here. perhaps it might not be trivial to understand them for the non-expert, but just remember that this is the way that you measure the size of these stars. Okay, I added some backup slides, so if there are questions, I will go through them. But just to say that these results are relevant, they are interesting to the community, and they have been proven to work. Also, in the recent months, I would say, CIEMAT has also led the upgrade of this system. So, so they equipped MAGIC. They modified the spectralon plate that we use to calibrate the telescope to measure the optical PSF, and they added a couple of optical filters to the spectralon, which is already in the camera. This means that you don't need to physically install anything to take stellar intensity observations. So right now, tonight, if we want, we can take intensity interferometry observations. So you don't need to equip anything special right now to the telescopes. The other modification that was done was a proper data acquisition system, which was also done here at CIEMAT by Juanjo. Sorry, before I did not say, but it was mainly Carlos and Juan Cortina, the ones that designed modification both at CIEMAT. So now we are properly taking data with a powerful machine, with a powerful digitizer, digitizing at 500 megahertz, and a GPU that performs the correlation almost online in real time, and essentially provides full duty cycle with no data loss. Before, with the oscilloscope, there were very high data losses. Now there is no data loss, and this system is really showing very, very good performance. Okay, so this is very, very, very preliminary results, but just to show that the system indeed performing as we expected. So the first measurements that we made look very consistent with the literature, with the measurements that actually Narabri did in the 60s. So here you can see essentially these are the coherence measurements that we make, and when baseline changes, so when the actual projected distance between the telescope changes because the star moves across the sky, so the distance between the telescope changes over the night. So it allows you to actually measure the size of the star. Okay, but not only that, we can use this star as calibrator to measure the zero baseline correlation, which is a value that we expect to be constant. And then if we assume this value to be constant, then we can perform observations on other stars with a very, very limited range in baselines. So here we cannot clearly do an unbiased fit of this model, but what we can do is assume what we are measuring is a star, a single star. So this baseline correlation will be constant, and then with the new measurements of the coherence at a given baseline, we can fit and we can get another measurement of another star, in this case, Alnilam. Okay. So the sensitivity that we are reaching is consistent with what we are expecting. So see backup slides if you want to understand a bit better what these plots are. Okay. Yeah. So very few points about as an stellar intensity interferometer. So it's actually a very interesting system because it provides very high signal to noise over a single baseline. So it essentially allows us to choose in which ranges of this curve you want to measure. Okay, so depending on source and depending on the science that you want to do, you might want to go to these baselines or these baselines. So, MAGIC has very high signal to noise at a fixed baseline. Probably MAGIC is right now the highest sensitivity interferometer in the blue right now. And if we added the LST1, which is right next to MAGIC, it would compete in sensitivity with amplitude interferometers. That would be amazing, and the amount of science that we could do would be enormous. So we have already a working setup. So we can add new optical filters. We can study different wavelengths, And also, this is something very funny that I will not discuss much about, but the fact that magic mirrors are robotic, they can be moved. We have active mirror control. We can essentially divide our telescopes into two virtual telescopes. No, so half of the light will go to one pixel, half of the light to another pixel. So we could literally directly measure in each of observations simultaneously these points here at a given baseline between the telescopes, and also the zero baseline correlation, which we would be correlating two telescopes on the same location, no? Which would literally dramatically improve our sensitivity to measure the size of stars, for example. No, so now we have done 37 minutes. I will very briefly go through some of the science cases that we plan to do, but I will not take too much time. Sorry if I go a bit fast, but I prefer for you to be able to ask questions and maybe go deeper into these science topics. Okay, so right now the top priority of MAGIC is calibration and making sure that everything works, not only because we need to calibrate our system, because intensity interferometry needs to be explored. No, so we are the first, for example, the first instrument that has active mirror control and performs intensity interferometry. So it makes sense to start exploring different approaches to improve the technique. No, so first we'll focus on stars that have already a known diameter, a diameter that has directly been measured. Once we see that the performance agrees with the expectations and that we are properly able to reconstruct the size of the stars that we believe we know, then we can go to new stars. No, so why is relevant to study the size of stars? Because knowing that, so directly measuring the light, their size, is the only way in which we can actually determination of their luminosity. Okay, and modern astronomy essentially relies on stellar models. Like all across astronomy, they use stellar models, and those stellar models use these direct observations as their initial points for the modeling. So it's not only that they are used to test if the models are accurate, not only that, no, it's that they are actually used to generate the models. So the effect of improving the measuring more stars and more types of stars will automatically improve the stellar models that are used all across astronomy. Also, for example, a very high impact science case right now, of course, it's exoplanets. So exoplanets, they are detected. You know basically what is the star that hosts a planet. You automatically are constraining also the physical parameters of those planets. Okay, so there is a very large scientific interest on something as boring and just measuring the size of stars. So other interesting projects that we can do is explore the synergies between stellar intensity interferometry and astroseismology, which studies the flickering of the stars and studies the different vibration modes of the stars that you can see, for example, here. So by using astroseismology, we can improve the astroseismology analysis, and perhaps in the future we could even make vibration modes. So if you to image one star with enough sensitivity, you could actually measure how it vibrates. We need an enormous amount of sensitivity, so be something more into the CTA realm. Another thing that is very relevant for exoplanets is to measure the limb darkening. I can go deeper into that if you want later. The limb darkening is essentially how, so stars are not a uniform disk of brightness. They actually are brighter in the center than on the sides. And actually knowing how that brightness is reduced as a function of the radius of the star is very relevant, especially for exoplanets. But also for understanding the modeling of stars, their internal structure, etc. So as we are so sensitive at a given baseline, we could this constraining the limb turning of a couple of stars is actually feasible for MAGIC, and that is something that would be extremely interesting to study. I will not go very deeper on it, but you can actually see that the same was done in the red in this reference. You can take a look; it's very interesting. So I'm already moving to the conclusions in 42 minutes. That's very good. I'm very happy with it. So during the last few years, CIEMAT had a leading role in demonstrating that the Stellar Intensity Interferometry is feasible with Cherenkov telescopes, okay? And the sensitivity that we are reaching is indeed consistent with what we were predicting. That's fantastic. So MAGIC recently upgraded its system and is ready to routinely perform these observations, mainly during bright moon periods. But if a transient of extremely bright transient appears, we are ready to observe. This means that during bright moon periods, we will have a lot of observing time. So luckily, we'll have plenty of things to study. And also, with the excellent sensitivity that MAGIC is showing, we are already able to produce novel science. So we have already measured the size of stars that have never been measured, okay, by anyone. And actually with very little observing time, which is the nice thing. So for all these reasons, now it's the ideal time to actually attract the attention of experts in stellar astrophysics. We are particle physicists, most of us, or very high energy astrophysicists. So it is a very interesting time for building new opportunities of collaboration between the different groups working on these topics. I would say that probably the most interesting ones right now are astroseismology and stellar modeling. But if anyone here in the audience knows anyone that could be interested on these measurements, please contact us, because we are in need of stellar astrophysics experts. And that's all from my side, so feel free to ask questions. And I expect all of you to be clapping.
Okay, Tarek, thank you very, very much for this talk. It really has blown my mind. I mean, didn't know this. The possibilities are really fantastic. We'll expect a few questions will come up. Let's see. I have one, but let's see if someone wants to. Yes, Alessandro, go ahead.
Hi, good morning. So my question is perhaps a little bit naive, perhaps a little bit, but from the perspective of an optical astronomer. So you commented that this technique is not especially sensitive. So basically, I guess my question is, what is the limited magnitude of stars you can actually get the emitter of?
Yeah, I actually forgot to add that figure, and probably it was one of the most important figures to be added. Yeah, so right now we expect in a few hours to already be able to study MAGIC-SII, which is of course extremely bright for an experienced astronomer, but it's actually not that bright if you think of interferometry. Okay, so now with MAGIC, we will be able to study stars of magnitude 5 and brighter. Things would enormously change if we added the LST1. Okay, if we added one more telescope, which is the first CTA prototype that is already operating and taking data in La Palma, could go down to magnitude 6 or even magnitude 7. So the amount of stars interesting above magnitude 7 it's already on the thousands. But yeah, so for most optical astronomers, they will those brightness are extremely high, are enormous.
Okay. Any more questions? You can either raise your hand or speak up.
Hello, quick question from La Palma. This is Mark Balcells from the Isaac Newton Group of Telescopes. Many thanks, Tarek, for this enlightening presentation. Very inspiring, especially for us who every day we buy the MAGIC and the LST-1 telescope, and we know you're doing things there, but we don't quite understand the depth of the new result we'll be generating. So this is very, very impressive.
Thank you.
Two questions. Can you obtain information not just on the size but on elongation of stars? So if a star has an accretion disk, for instance, or if it has jets, what would you need to be able to characterize those elongations? And a second question. I know your presentation is on intensity interferometry, but can the Cherenkov telescopes be used as phase interferometry too? And what would be needed for that?
Okay, so first question. So yes, we would be able to measure the elongation of a star or any bright structure called the OB stars or BE stars. We know that there will be disks, so we can definitely go for those disks. The technically it depends, because when you only have to, unfortunately I don't have the slide in the backup, but when you only have two telescopes, you are only studying one line of sight of the star. Okay, so you can actually see me right now. Well, I don't know. So when you have a star, well, maybe I can go to a slide in which I have a star here. I don't have it as backup. Maybe here, for example. Okay, so imagine that we are measuring this star here. So if you only have a telescope pair, then the only measurement of the size that you can do is on a specific direction, which is the direction projected to the two telescopes. Okay, so as the moves in the sky, the projection of the two telescopes rotates, and you are essentially making measurements of this length, of this distance. No, so with only two telescopes, generally for most stars, the range of, let's call this angle azimuth, so the range of azimuths that you measure is not that wide. If you have 3 telescopes or 4 telescopes, you are simultaneously measuring many directions in azimuth. So you can definitely measure the elongation of stars, their oblapness, and this is something very relevant for the bright OB stars that we measure, because they are the brightest in the blue. Because they are extremely fast rotators, so it is known that they are very oblate. So we can definitely do it. If there is a decretion disk, something, any structure within the star, it will be of, let's say, smaller scale, which means that we would probably need larger baselines, no? And this again falls into the probably of CTA, and we do expect that CTA will indeed be able to measure decretion disks. Regarding this second question on if CTA could theoretically behave an amplitude interferometer as the other optical interferometers, I'm an expert of amplitude interferometry, but I would say that most certainly not. There is why is first, it would be extremely expensive, but I would say that the most reasonable reason why it would probably not be possible is because the actual optical quality of the telescopes is so bad that the optical PSF, the actual size of the spot of these telescopes is literally like this big, so it's centimeters scale, no? And collimating such an enormous beam is extremely difficult, extremely difficult. So when I was referring to this astronomical quality of the mirrors and of the system, I was referring exactly to that. So we have such uncertainty on the actual direction that the photons are coming from. It would be extremely challenging to do that. And I would say that even if we did, it would be so expensive to combine physically the different light beams that it's something that is definitely not on the table.
Okay. More questions? You can speak up or raise your hand. I do have another one in the meantime.
Sure, feel free.
To perform one of a characterization, I mean, this is a very broad question because what does it mean to characterize a star? But of a star, I mean, what is the typical, how many hours would you need typically to make a study of a single star? So at some point, can you make like would you be able to make with the few days that you have each month to make statistical analysis of populations of stars, or is it really, you know, focused studies on?
So we will be able to do a catalog. So we will have statistics. Very briefly, so data runs generally are 5 minutes or 10 minutes per observation. We might several runs, of course, from a given star, but generally with 10 minutes of data of the bright star we're measuring right now. Okay, we are focusing for the moment on calibrators, which means that they are rather bright. We are usually detecting them in each of these 10 minutes runs. Okay, so it is actually not that hard to have a very decent number of stars measured. Of course, it strongly depends on two things: on the science that you want to get out. As I was talking about, for example, this limb darkening, as you can see in this star here. If you want to simply assume that this star is a solid disk, okay, with uniform brightness, just determine the radius, it will require a very little amount of time. Of course, on that number to have a 1% uncertainty, they will need many hours of time. If you are okay with 10% uncertainty, then with maybe 20 minutes of observation is enough. But to differentiate between a solid disk and a limb darkening profile, so if you want to differentiate between these nicely changing intensity as a function of radius with respect to a uniform disk, then you would need way more hours. So this a study that we could only achieve on a couple of very bright stars of the exact size that is suitable for our two telescopes, etc. If we added LST1, then things would dramatically change. The amount of stars that we could study would increase, I would say, very significantly. And of course, if you think about CTA, then the amount of things that you can do CTA is really enormous. But I can say that right now for MAGIC, we are taking routinely data, and most of the stars that we have observed, we have measured their diameter quite precisely on the 5 to 10% level in uncertainty, and things seem to be working very, very well. So if there is one source that is especially interesting, or for example, a population of sources that is especially interesting for a specific study that is relevant, for example, in the blue, which is the main wavelength range that is new, then feel free to contact us because we will be able to take the data.
Good. Thank you. Okay. More questions?
Hi, yes. So this is Martin from CIEMAT. So you said you have. I'm just curious about this. You said you have a backup slide explaining this, the reason why you are sensitive only to one wavelength. If I remember correctly, you could explain it a little bit. I'm just curious about that.
Yeah, so I want to stress again how complicated interferometry is. The best way for me to explain it is for those of you that have experience with the Fourier space. So you can actually imagine interferometry is performing measurements on the Fourier space. Okay, so if you have you transform it into the Fourier and you remove some frequencies in the Fourier space, then if you try to reconstruct back your signal, many frequencies have been lost and you will never be able to know what they were in the past. No? So with interferometry happens exactly the same thing. And what frequency you measure in the Fourier space comes from the distance between the telescopes that you correlate. Okay, so then if you have, here is a very nice example. If you have short baselines, meaning telescopes that are very close together, if you go to the lambda over baseline formula, then it means that you have enough resolution to study large stuff. And if you have many telescopes that are very far away, then you have resolution to study the small stuff. So in this image, for example, in both images, you have long baselines, meaning that you are able to study the small stuff. And in this image in the right, you can see the very fine structure in the image on the right. No? But these bright lobes that you can see in the image in the left, it's only possible because you have short baselines. No? So I could, for example, say, give an example of in this star that we were talking about before. Imagine that this star was significantly bigger, but there was a very bright spot in the center. No? So if that bright spot falls the resolution that you study with the MAGIC telescopes, for example, you would be able to study that, but know the actual size of the big star. So it is very, very difficult to actually interpret that spot because you don't have the big picture. You don't have where that spot is located in the star. You don't know if that spot is in any location of the star, and you don't know even if there is a star there. You simply don't have information on those distances that you are not exploring. That's why CTA would be extremely interesting, because it has so many telescopes that the range of baselines that will, because you have to understand that each telescope provides many correlations. No? So this means that the measurements that you do in the Fourier space cover a very wide range of resolution. So the prospects for CTA are extremely interesting.
Okay. So you had understood correctly. So the problem basically would be coming from the fact that you have like a fixed baseline, right? So you are so you have that you are sensitive to that mode in the UV plane, right? But that could be solved by like switching on and off. If you have several telescopes, you have different combinations of baselines, I guess, right?
Exactly. So if you add more telescopes at different distances, then the amount of baseline scales that you can study, it's much wider. Of course, this is not a 1D problem, as we discussed before with the oblateness of a star case. It is not always a 1D problem. It is usually a 2D problem. So we call that UV. That's the UV plane, and you only have two telescopes. You are just measuring a couple of points in the UV plane that are moving. If you translate that to one dimension, is these plots that I'm showing here as a function of baseline. But when you have two dimensions and you have many telescopes, the amount of points that you have is enormous. And that means that the amount of information you're getting in the Fourier space is very high. So you would be able to reconstruct properly the original image, let's say.
Okay, great. Thank you.
No, thank you.
Okay, I think we can fit in one more question. Let's see. Anyone wants to speak up? All right.
Interferometry is
Yeah. but also impressive as for the results that you can obtain. This is really great. So yeah, we thank you again very much, Tarek, for this presentation, which will be available to the agenda page, as well as the recording. So see you next time, and I thank you all for coming.
Ciao, bye-bye.
Bye.